All right, let's talk about work when it's being done by a non-constant force. It was really simple when it was a constant force. We had a certain amount of work, a certain force exerted over the entire distance. We dragged that box like 10 meters, and so all we had to do is calculate the work by taking the force and multiplying by the displacement. This force, by the way, is only the part of the force that's actually causing the motion. So I should have didn't quite match that up, did I? So what we were really doing is finding the area under this curve because it was a rectangle. So we take the height times the distance. So the way to handle a non-constant force would be to get a graph of that force versus distance traveled. I could call this a d or an x. It doesn't really matter. So if in the situation that she was talking about in the video, what if we started really fast, but then lost force as we went? We got tired as we went. Well, then we'd have to find the area under this curve right here. And it's triangle, so we would have the work being 1/2 of the maximum force, the altitude of the triangle, times the distance traveled, which is whatever x is. So you just got to find the area under the curve. Now, this gets to be a little harder if the shape of the curve is some sort of wacky thing. I mean, if it's piecewise continuous, like it's this number, and then it drops down to this number, and then it ramps up to this number, and then it stops. I mean, we could find the areas under each of these sections. Probably have to cut this one up into a triangle and a rectangle. Rectangle, 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 triangle. We could probably do this bit by bit to find the work. But what if the graph was some sort of craziness? You know, like what if the graph was, what if f was equal to, x squared somehow, or proportional to x squared, I should say. Then we'd probably have to switch over from finding the area under the curve into doing an integral. And this is something you're going to learn how to do in your calculus class. The integral is a mathematical process that finds the area under a curve by slicing it into really fine little rectangular segments, finding the average value of each of those tops, and then adding up all these rectangles. And the process, this adding, starts as a sigma, so the work would be the sum of all the individual f's times all the individual little x's. But when you do an integral, the sigma sign turns into a kind of a smooth S shape. Sigma means addition in mathematics. It turns into a smooth S shape, and then you have your f, and now the x is now little tiny dx's. D stands for delta, and the original symbol was actually the lowercase Greek delta, because uppercase Greek delta means a change in, right? So this means change, and this is a lowercase one, so this is a little change. And these were the little delta x's right there. In the modern notation, we don't use the Greek letter, we use the letter D to represent delta, lowercase delta. But it is a small d, so it's a small change in, well, in this case, it is distance. So you're going to use a area under the curve approach, with this as being the basic recipe, when you have a non-constant force, even if you have to carve it into pieces, as long as the function is piecewise continuous. But when you learn in your calculus class about the integral, then the work done is just the integration of the force over the distance. And that'll work for any function of f that you could possibly write down.